Let's wrap up this series with a discussion of how to tune window functions. Welcome to this video on window functions. My name is Kevin Fiesel. I am the proprietor of Catalyxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. Throughout this series, I've focused on practical aspects of window functions, namely how they work and the specific mechanisms you can use to generate the results you desire. What I haven't done is take a detailed look at how window function queries perform or how you can potentially make them go faster. That's the purpose of this video. Let's head to the classroom first before jumping into a demo. In this classroom segment, I want to talk about indexing strategy with window functions. The rule of thumb around indexing window functions is POC. First, we focus on partition by columns. Then, we look at order by clause columns. Finally, we review covering columns. That is, all of the other columns that appear in this query. This guidance is reasonably sound in a bubble, but I want to make an important addition. Where clause filters need to show up prior to the POC columns. If you have a great filter on a where clause, that can limit the amount of data you're sending to a window aggregate operator. When we get to the demo segment, we'll see how this can make a significant difference in query performance. The next thing I want to talk about is batch mode. Batch mode has been in SQL Server since 2012, but it really came into its own in SQL Server 2019. Batch mode gives us some great capabilities over row mode. Row mode, as the name implies, processes one row of data at a time. Yes, even in your set-based queries, everything eventually boils down to processing single rows at a time. But with batch mode, we can process 64 kilobyte blocks of data, or up to 900 rows at a time in a single batch. We evaluate metadata once per batch rather than once per row. That means, at the extreme, instead of performing metadata operations 900 times, we perform them one time. And if there is a function that operates on the batch, it can handle all of the rows in the batch at once, rather than operating on each row individually. This can lead to significant performance improvements without changing your code or having you even think about it. But there are rules around when something can go into batch mode. There are two branching paths that we can follow. The first branching path is, do you have a column store index on that table? If so, SQL Server can check if the expected batch mode cost of the operation is lower than the expected row mode cost. If that's true, congratulations, SQL Server goes into batch mode and you get yourself a free speed boost. But let's say you don't have a column store index on the table. Well, if you're in SQL Server 2019 or later, you can still kick it up a gear, but only if you meet all of the following criteria. First, you have a row store index. Second, you have at least 131,072 rows in at least one table in the query. 131,072, by the way, is 2 to the 17th power, in case you were wondering why the weird number. Third, you must have at least one operator that benefits from batch mode. Not all operators benefit from batch mode, after all. Fourth, at least one input of a batch must have at least 2 to the 17th rows. Now, this may sound like repetition of the second line, but it's really not. If you have a table with 10 million rows, you have satisfied that second criterion. But if you have an extra selective filter that the optimizer believes will return a single row, batch mode will not trigger. Finally, the expected cost for batch mode must be lower than the expected cost for row mode. If you meet all 5 of these criteria, then your query can go into batch mode. Now that I've described these two scenarios, let's go into a demo and see them in action. Here we are in SQL Server Management Studio. I've switched things around a bit to make it easier to read performance metrics, and SSMS does a better job of this than Visual Studio Code, at least as of the time of this recording. In this demo, my goal is to go into moderate depth on performance tuning and window functions. If you want to go deeper into the topic, check out the links in the description below, as I have a link to Itzhak Ben-Ghan's excellent book on T-SQL window functions, as well as several videos from certified pretty okay guy Eric Darling. I don't want to go to the same level of depth as what Eric does, so instead I'll give you the higher level description and let interested people check out Eric's videos for a lot more detail. That said, let's start by checking the compatibility level of the Wide World Importers database. I want to make sure it is at least in the 160 compatibility level so we can take advantage of batch mode on row store in SQL Server 2019 or later. I'm also going to drop an index on the invoices table just in case I had it there to begin with from prior testing or prior runs of this demo code. My first script is a simple one. I'm getting the row number for each customer sorted by order date ascending. I've put this in a common table expression for exactly one reason. So I do not need to spend time writing the results out to the screen. I'm interested in the performance of the query and not how long it takes Management Studio to display the results. I already have include actual execution plan on, so let's run the query. We get no results back, which is what I want. Let's switch over to the execution plan tab. This query did not take very long, just over 50 milliseconds or so. But there are a few things I want to point out. First, this query went parallel and took advantage of multiple CPU cores. Second, if I hover over the clustered index, I can see that this query ran in batch mode rather than row mode. Right now, I'll simply assert that this is a lot better, and we'll see some examples in a little bit of what a difference this can make. Third, after our scan, we need to sort the data. Hovering over that operator, we sort by customer ID ascending and then order ID ascending. After that, we send the results to a window aggregate operator, and this generates row numbers for us. The filter is there at the end to prevent displaying any data and forcing us to factor in the cost of writing out to screen. Now, 56 milliseconds, or however many milliseconds it happened to be in this particular run, that isn't terrible, but we can do a little bit better. I have here an index on customer ID and then order ID, following the guidance from the classroom segment. First, we start with the where clause filters. We don't have any of those, so we move on to the partition by column, customer ID. Then we add the order by column, which in this case is order ID. And we have no other columns necessary to cover this query, so we have nothing to add to the include section. It'll take a moment to create this index, and after it's in place, let's run the same query again. This time around, it's going to take around 35 milliseconds to complete. This is not a slam dunk right home to mom kind of result, but for a busy enough query that runs often enough on a busy server, it can add up. Also, mousing over each segment, each of the 3 operators processed in batch mode, which is something we want to see. But what happens when somebody decides to flip the script on us and sort by order ID descending? Well, we're not quite back to where we were originally, but it's close. We have our index scan, so it did pick up the index correctly. But now we need an expensive sort operator before we can feed results into the window aggregate. This is an important indicator that ordering absolutely matters for window functions, and having the wrong sort order on your index can lead to subpar performance. But what happens when we have a valuable where clause? In this case, I'm only looking at row numbers in situations where we have at least 3 chiller items. Let's check how many invoices we have and how many of them had at least 3 chiller items. Running this query, we can see that of the nearly 667,000 invoices, only 44 have enough chiller items for us to care about. This means that we have a very selective filter criterion. But when I run the window function query, we see a common story in SQL Server processing. The clustered index scan has a fat arrow pointing to the left, and that typically indicates relatively large number of rows this operator thinks it processed. If I mouse over it, I can see that we sent 44 rows, but we had to process almost 667,000 rows to get to the 44 that we sent. Tools like SolarWinds Plan Explorer will tell you when you have this sort of inefficiency, but this is obvious enough that I can spot it in SSMS on this particular query quite easily. Also, note that we are performing a clustered index scan, not even using the index that we created. This is because our index does not include total chiller items, so we would need to perform key lookups for each row to read from the non-clustered index back to the clustered index, and then retrieve the value of total chiller items for each invoice. That's even worse in terms of efficiency, so instead we just scan the clustered index to get all of the details. Let's change this index here, putting the contents of the where clause in front of our index columns. I'll use drop existing to recreate the index that I know already exists, and once that's done, I can rerun this query. This time around, looking at the execution plan gives us a much better result, taking under 1 millisecond because we have narrowed down to the 44 records we need. At this point, we no longer have enough rows for batch mode to kick in, so these are row mode operators running on a single CPU core instead of processing in parallel. Now that I'm done demonstrating that bit, let's drop the index we created, as I won't need it for this next part. For this next part, I've already mentioned batch mode a couple of times, but I'd like to give a practical demonstration of what batch mode can do for us. As we learned in the classroom segment, batch mode on row store in SQL Server 2019 or later requires a certain number of rows to trigger. I'm querying the cold room temperatures archive table, which on my Wide World Importers instance has approximately 40 million records, as we can see from this query. That'll definitely be enough to trigger batch mode. What I'd like to do now is run the next query prior to my explaining it. Okay, what we're doing in this query is, I want to generate a row number from the cold room temperatures archive. This is a temporal table that stores a history of cold room temperatures for various truck freezers. I want to partition the data by cold room sensor number and sort it by the temperature ID ascending. Just like before, I'll wrap this in a common table expression and return where row num is equal to 0 so that we do not spend any time trying to display 40 million results. The last thing I want to note is that the query plan hint says to use optimizer compatibility level 140. This forces row mode operators for the query as we do not have a column store index on that table. The query will take approximately 15 seconds to complete, but once it does, I can switch over to the execution plan. The right side of the plan is slightly weird, but we can see that it takes approximately 10 seconds to retrieve all of this data, approximately 2 seconds to sort the data, and another couple of seconds to execute the segment and sequence compute operators. Now let's run the query again, but this time I'll leave off the query plan hint. This second run of the query is still going to take some time, but it should not take nearly as long as before. I will note that I've had this second query return anywhere from 3 to 8 seconds. The primary difference here is in how long it takes to scan the cold room temperatures archive table. So for the sake of future me recording the demo video portion, I'll assume that it took about 3 seconds and I'll look like a buffoon if it really took 8. Digging into the execution plan for this, in my pre-recording testing of this query, it took about 1.4 seconds to scan the cold room temperatures data. If I mouse over the clustered index scan operator, we can see that it did in fact use batch mode as we wanted. The next thing we can see is SSMS is not displaying times quite the same way as before. With row mode operators, we will see increasing times from right to left as each operator includes the time of its child operators in its own calculations. But in batch mode, that doesn't always happen, as we can see here. We spent approximately 1.4 seconds reading cold room temperatures, but the right anti-semi-join hash match operator indicates approximately 40 milliseconds of time spent. That behavioral difference can be tricky, so watch out for it. We still spend 1.5 seconds sorting the data before our window aggregate, so that's the other large chunk of time. But if you think about it, switching from row mode to batch mode saved us about 12 seconds out of 15, and that's a pretty significant performance improvement given that I did no work at all. For this next set of queries, I'm going to describe them first and then switch to a different tab where I've already run them. You'll see why in a moment. I want to look at another example of how batch mode can save a lot of time, as well as show a performance difference between rows and range. Here, I have a query that gives us the sum of temperature, partitioned by cold room sensor number, and ordered by cold room temperature ID. Remember that the default frame for an aggregate window function with an order by clause is range between unbounded preceding and current row. I'm also going to force row mode operators by setting the query optimizer compatibility level to 140. In the next query, I'll switch from range to rows, but keep everything else the same, including the remainder of the frame and the query hint. For the third query, I'll go back to a range frame operator, but open up the possibility of using batch mode operators. And the fourth query uses rows as a frame operator and enables batch mode. Now let's switch over to this other tab where I have query results already queued up. The reason I wanted to run this off screen is because it takes several minutes to complete, and you really don't need to see me twiddling my thumbs for all of that time. The 4 queries took, in total, 2 minutes and 4 seconds to complete. Of that time, range over row mode took by far the longest at 89 seconds. Then, rows over row mode took 27 seconds. Range and rows over batch mode were just shy of 4 seconds. These are some enormous differences, so let me explain why we see what we do. For the first 2 queries, they start out the same way, taking approximately 12 seconds to read all of the data and then a few seconds to sort. Both of these sorts have the same memory grant and spill in the same way, so there's really no difference so far. Then we segment the two, and you can see that the range segmentation takes just a little bit longer than rows, but that's nothing too wild. And still, at this point, range and rows, they are within 2 seconds of one another, and almost all of that is just in how long it took to sort the data. Scrolling left to match these up, we see our first difference. In the range query, we move from one segment to another segment, and the second segment takes approximately 1.5 seconds. In the rows query, we perform a segment, then a sequence project, and then another segment. By the time we're done with that second segment, we are at 17.2 seconds, which is very close to range's 18.3 seconds. Now I'll drag the scroll bar for the second query all the way to the left and match us up again. From here, both queries require a window spool. That window spool is how SQL Server keeps from needing to scan the data over and over. It loads the processed and sorted data into its own internal space and can scan that spool for each cold room sensor number. But notice how it took 4 seconds for the rows query to finish creating its spool, yet it took the range variant more than a minute to do the same task. This is because SQL Server needs to do additional checks to see if there are any ties in the combination of partition and order by clauses. It turns out that cold room temperature ID is unique, but the database engine can't make that assumption, so it needs to perform expensive checks for each row. Specifically, it needs to use a disk-based work table instead of an in-memory work table. If I switch over to the Messages tab, we can see the results of set statistics IO on to verify what I'm saying. For the range query, we have a work table that includes 40.2 million scans and more than 361 million logical reads. For each row in the table, we need to scan and see if there are any other matches on cold room temperature ID. By contrast, the rows query has a work table that has 0 logical or physical reads because it was all able to happen in memory. As a result, rows is considerably faster than range when we work through a large number of records, like in this case. And as you might recall from the earlier video on running totals, we typically want to use rows as our frame for aggregates because it gives us more human understandable results. For this reason, you might want to default to rows unless you know you need range. But I say might want to because of the next bit. If we're in batch mode, the results are effectively the same. SQL Server doesn't need an on-disk work table, so we don't have an explicit window spool, nor do we need to scan the spool for each record. This means that there is no practical performance difference between rows and range when you are in batch mode, at least as we see in this query. Thus, if you know your query meets the criteria for batch mode, the choice of a frame doesn't matter nearly as much for performance, but it still matters for business correctness. Now let's switch back to the first tab and finish things out. My next piece of advice for performance tuning is to limit the number of unique windows that you're using in a query. In this case, I'm generating 5 row numbers off of the invoice lines table. I'm partitioning by invoice ID, then stock item ID, then package type ID, then tax amount, and finally, line profit. If I run this query, it will take a few seconds because we are writing 1.7 million rows to screen. I could have wrapped this in a common table expression and filtered so that we don't see any of these, but it's fast enough, and I just finished vamping, so I can switch over to the execution plan tab, and we'll see what is interesting. These are all batch mode operators, thankfully, but notice that we need to sort and then perform a window aggregate for each of the 5 windows. The sorts add up to the large majority of wall clock time, but they are necessary because we asked for 5 different sortings of the data. And the worst part of this is that there isn't a clever index that will solve the problem. We can make the first sort better, but that's all we can do. Also, like we saw before, order matters for Windows. I have here two row number function calls. Both of them partition by the invoice ID, and they both order by invoice line ID. But the difference is that the first sorts by invoice line ID ascending, and the second sorts by invoice line ID descending. If I run this query and switch over to the execution plan, we can see that there are two sorts and two window aggregates. This, again, uses batch mode, so the net result is a query that finishes in well under a second. But because we have two different orderings of the data, we can't create a single index that satisfies both of these. The best we can do is add an index on invoice ID and invoice line ID and remove the cost of the first sort operation. But what happens if you have multiple window functions using the same window definition? Well, we saw this earlier in the series, but I think it's fair to bring up again. In this case, invoking row number, rank, and dense rank over the same window definition nets us one scan of the index and a single window aggregate. We can generate a proper result without needing multiple window aggregates, and that's nice for performance. But what happens if we add in other types of window functions, like say aggregate window functions? In this case, we still have the same window definition, partitioning the data by invoice ID and then sorting by invoice line ID ascending. But if I run this query and view the results, we can see two window aggregates. The first window aggregate is responsible for our ranking window functions, row number, rank, and dense rank. The second, meanwhile, covers our aggregate functions. These are batch mode operations, so they don't add a lot to the query response time, but this kind of thing can add up over time. Next up, let's remove the ranking functions. If I do that, the execution plan changes a bit. Now, instead of scanning the invoice lines index that happens to cover this query, the query optimizer has decided to make use of a column store index. This is a costing thing rather than a window functions thing, so I'll elide over it. But we do have a scan, and then our window aggregate happens in approximately 10 milliseconds. We also only have one for all of the aggregate window functions. And by the way, the specific aggregation column doesn't matter so much for this. In the final query, I'm summing quantity, getting the min unit price, showing the maximum tax rate, and getting the count of quantity. After doing all of this, the execution plan is exactly the same. This shows that, at least for aggregate functions, it's the window definition more than the column you select for aggregation that really matters for performance. I hope you've enjoyed this series on window functions. Over the course of this series, we've walked through the concept of window functions, including how we can tell if something is a window function or not. We've walked through all of the window functions available in SQL Server through SQL Server 2022. We've covered a variety of use cases for window functions that can help you solve common, and sometimes uncommon, business problems. We've hit upon some of the limitations of window functions, and in this video, we saw some ways to make window functions perform better. We'll have links and show notes in the description below. Until we see each other in the next video, take care.